Okay, thank you. And I will talk about actually about the work of two PhD students from ETH.
They are students of whom?
Okay, so both of them are students of a professor that, I'm sorry, I forgot his name. But Uli Wagner, when he was in ETH, was Professor Anden that works in his group.
Emovelzi.
Yeah, so actually they work with Uli.
Emovelzi is the guy.
Yeah, exactly. Thank you. And they worked with Uli Wagner. And so Anna Gundert and May Szedlak. On the two girls, she just finished her master's and she now finished her PhD. So let me start with a reminder about the graph case. So in graphs we have some finite graph. We have the Laplace operator on functions on the graph, which is for a given function f, the degree times the function at this value minus the sum over all the neighbors u of v of f. This is the Laplace operator on the graph, and there is always, this is a it's a positive operator, and there is always a zero in its spectrum, so the constant function c will always give 0. And it will be the only 0 if and only if the graph is connected, so 0 as multiplicity 1 if and only if G is connected. So from now on, let's assume that it's connected. And then we can ask about lambda x, which is lambda g, sorry, which is the minimum over the spectrum, which is just the eigenvalues. Okay, I'm writing spectrum because I'm used to it. The Laplacian restricted to something which is orthogonal to the constant functions, and that is going to be non-negative, and if the graph is connected, then actually positive. And we want to estimate this thing with respect to the Cheeger constant that I will describe in a minute. So this is one thing that we have, and the other thing we have is the Cheeger constant, or the version of the Cheeger constant, which is given by the following thing. So we have the minimum over all partition of the set of vertices V into two sets, both of them not empty. I'm writing it in a bit stranger way because this is how I'm going to generalize it. So what we have is the number of vertices, the number of edges between A and B, divided by the size of A times the size of B. So B here is actually, in this case, just a complement of A, right? Because it's a partition. And we asked about this thing, which is some kind of an expansion of the graph. We asked basically what is the least number of edges that can be between any partition of the graph into two sets. And we want to estimate actually this thing, and now the Cheeger inequalities tells us that lambda of G is bounded by H of G, and from above, and from below by h squared divided by h times k, where k is the maximal degree. So this was a very quick reminder about the graph case. I hope all of you already saw it at least once. I'm not going to prove it. And basically what we are trying to do now is we are going to talk about simplicial complexes. And we want to try and generalize this thing and the Cheeger inequalities. And we will actually talk only about this one because this turned out to be much harder. We are still working in this direction, at least for the for skeletons without a complete, for complexes without a complete skeleton, this doesn't exist. Okay, so I will talk about it in a second.
So this part is actually Boozer.
This is Boozer, and one inequality is Boozer, and the other one is Aron-Milman, right?
Well, Boozer is in the context of manifolds, and I think Aron-Milman in the context
Aron-Milman is in the context.
It's the same inequality. Aron-Milman, the
Boozer did it in the manifold
Manifold.
case.
right, but the
So Cheeger did this in the manifold case, Boozer proved this one in the manifold
no,
case,
in the
Aron-Milman proved this
No.
in the graph case, I think.
no.
No?
Aron-Milman proved what Boozer proved.
This one.
No,
No,
This one, sorry.
Yeah.
Yeah.
So this is what Aron-Milman proved, and also Tanner.
Mm-hmm.
And the other side was proved by Alon.
Alone. Oh, so, yeah, I'm sorry. There are a lot of people that worked here. I'm
What?
not making
Doju.
Also Doji?
Doju.
Doju.
Doji.
Right, thank you. So,
But there is a question, what is the right normalization if the graph is not bounded degree?
right.
We should be little aware of that because maybe the definition of the Cheeger constant.
Okay, so in the case where it's not bounded, there is another version of the Laplacian where you take the square root of this, the degree of both vertices of this edge, and then in this case, in the Cheeger inequalities, this k disappears. You have here only a number. And I think this is somehow the right way to discuss it when the degree is not bounded. Because then somehow this is swallowed into the Laplacian in some sense. But yeah, there is here an issue how to normalize in the case where the degree is not bounded. But I'm going to talk about the finite case and that. So yeah, Chang usually works with this version of the Laplacian, the square root of both degrees. Okay, so I don't need to define what is a simplicial complex, right? So X is going to be a d-dimensional simplicial complex. And let's start with the assumption that X has a complete, full d-1 skeleton, namely we have all the d-1 and lower cells in the complex, and we only decide for example, in a triangle complex, this means, in a two-dimensional one, this means that we have n vertices, we take a complete graph from them, all edges, and then we decide which triangles to put. In this case, we have this definition. So h of x, we are trying to generalize this thing, is going to be the minimum of a partition of V into d+1 sets, all of them non-empty. And then, okay, so we have here the size, we have here the size of the sets, just like that. And here what we have
is 0
D. So we have the number of D faces which has one vertex in each of those sets. Okay, so for example, in a triangle complex, let's say that we divided all the vertices into those three sets, and then we ask how many triangles can we find with one vertex in each of those sets. So this is the generalization we have in the case of a complete skeleton. And now we have this theorem which says that this is joint work it Parzanchevski and Tassler form. Okay, it was here. And we proved it. Then in this case, if X has a complete skeleton, then lambda of X is smaller or equal to h of X. I didn't define lambda of X, I will define it in a second. But you should think about it as a generalization of the spectral gap here. Okay, so this is what I'm going to do now. But we have the upper bound. This is what the theorem says. So let me now describe you what is the spectral gap and the Laplacian in the I-dimensional case, and then we will discuss what can be done in the case of a non-complete skeleton. So this is the work of Ekman's from the 40s, I think. And he defined the I-dimensional Laplacian in the following way. And so I'm going to give you a very short summary of this thing. I'm not going to develop it very carefully with all the details, but let's start by doing that. Okay, so let's define the space of one-fourth on our complex. Now, not necessarily with a complete skeleton. It's the functions from oriented J cells in the complex. I will explain in a second, such that the value on oriented cell in the opposite direction gets a minus of the value. So this is. I'm sorry, but I don't know the background. Did you define those things?
Not really.
Not really. Okay. So, what is a J cell? A J cell in a complex is just a subset of J plus 1 vertices. So let's think about a triangle complex. We have X, which has X0, the set of vertices. We have X1, the set of edges, which are just, so here we have, let's say, V0 up to Vn. Here we have some subsets of pairs, V1, V2, let's say V1, V5, I don't know, whatever we have. And triangles, this is triplets. So we have, not all the triplets, V1, V2, V3, and so this means that we also need to have, okay. And the only assumption we have is that if we have here, what is a complex, if we have this subset, then we have also all its subsets. So for example, V1, V2, V1, V3, V2, V3, and so on. Okay, so you are closed under taking subsets. This is basically a complex. And what are the oriented ones? So basically, it's ordered pairs up to an even permutation. So what we have here, we take all now ordered ones, I don't know, such that this belongs to xj, taking them with an order, and I divide by up to an even permutation. So, for example, in edges, if we have the edge xy, then now this gives us this oriented edge, right? Which basically is oriented from x to y in our complex, and we have yx, which is the edge oriented from y to x, and since they are not an even permutation of one of the other, they are these two different orientations. Let's see what happens in the triangle. So here we have 6 different possible orientations, and we have this one. So if we have a triangle, think about it like that. We go from x to y, from y to z, and from z to x. But basically, this is also going from y to z to x. And this is also an even permutation, one of the other. And this is also zx1. And we have the other permutation, which is xzy, which is the same as zx, which is the same as yx z. And this is going like that. Okay, so those are permutation. Basically now, for everything we have 2 permutations except for vertices. Vertices, there is no permutation because there is no way to order them. So what we have here, okay, so xj plus minus is size is going to be exactly the size, twice the size of xj when j is greater or equal to 1. And for vertices, we just define this to be a set of vertices because there is no limitation. Yes.
So all the functions.
Okay, so now back to the functions.
Okay.
So we have a function from xj, from oriented j cells. Think about triangles all the time, it's much easier, or on edges. Okay, so we have a function from oriented triangles to R. And we say that such a function is a one form, and we denote it like that. If, whenever we take f and evaluate it on some oriented J cell with some orientation, okay, let's put it like that, it's going to be the same as taking f on the same J cell with the opposite orientation, but with a minus. Those are one forms. Okay?
I'm just asking what
Yeah.
happens for points.
For vertices?
Yes, for vertices.
So then it's just functions.
Okay.
So omega j, omega 0, x is going to be just functions from x0. This is this. So now we have a chain complex. So let me just define an inner product on omega j. For f and g in omega j, we define the inner product to be the sum of sigma in xj of f sigma g sigma. And now, one point to notice here. Here I wrote xj and not xj plus minus. So it's not well defined as written. But since the value of this thing is independent of the choice of the orientation, what I mean is take each J cell, choose one of its orientation and evaluate this. Okay? This is independent of the choice of the orientation, and therefore we can define it like that. And now we have here omega 0x, omega 1x, omega 2x, and so on. And we are going to define a chain complex as follows. Basically, I'm going to define it only let's start with going down. So omega j is going to be, delta j is going to be from omega j to omega j minus 1. It's defined by the value on sigma is going to be the sum over v, which is the neighbor of sigma, I will explain in a second, of f v sigma. So there are a few things here that I need to explain. Sigma here is an oriented J cell, J minus 1 cell, some oriented J minus 1 cell. By V sigma, what I mean is the oriented J cell given by putting V in the first place. And what I mean by this thing say that if I add V to sigma, I get something which is a J cell in the complex. So let's draw a picture. Let's say we have those 5 vertices. And now let's say that I have this triangle, and also this triangle underneath. Okay. And let's say that we are here. This is V0, V1, and V2, V3, V4. Here we have f, which is some function, but let's assume that f is a function on oriented triangles. And now I want to estimate what is this thing on some edge here, let's say on the oriented edge V0, V1. I'm basically going over all vertices which form together with it the triangle. We have here only one, this one, so V2. And what we get is actually f of V2 at V0, V1. In this case. Okay, because this is the only triangle that contains V0, V, this edge. Is it clear? So I'm not going to show it to you, but it's not hard to see that this is a chain complex, meaning that this is 0. And now we can define subspaces as follows. So Vj is going to be the image of Dj plus 1. Zj is going to be the kernel of Dj. And since it's a chain complex, what we have is that the image of this one is always in the kernel of this one. And therefore, we can define Hj to be that ratio. So this is the first part of the theorem. Now, since we have here operators between those spaces and we have an inner product, we can talk about the dual. So let me denote the dual by delta here. We can ask what is the dual, and it's not hard to check. And the dual is given by the following formula. So this is from omega j minus 1 to omega j. And delta jf of sigma is going to be, so let me remind you now, sigma is the J cell. So this is something of this form. What we get is that this is given by the sum from 0 up to j of minus 1 to the I, f of sigma minus sigma I, where sigma minus sigma I is what we get by removing sigma I. So let's see here an example. What is, now let's think that f is a function on edges, and we want on oriented edges, and we want to see what it gives to some oriented triangle. So delta jf of, let's say, this one, v0, v1, v2, what we get is basically f of, first I am removing v0, so what we get is v1 and v2. Now with a minus, I remove v1. And finally, I'm removing v. So this is what we get. This is this one. Basically, what we get is the value on this edge minus the value on this edge, which is the same as taking the value on this edge, and then on this edge. Basically, we get this sum of stuff. Good. Now, since those define the chain complex, also the dual defines the chain complex, and we have this thing, I hope. And we can also define here Bj to be the image of delta j. We can define Zj to be the kernel of this one. And by the same reason, we have that Bj is something of Dj, and therefore we can define the ratio homology. Okay, and so it's a lot of notation. I'm just doing it very fast, and if you didn't see it, it's probably very confusing. But we are almost done. We have all those things, and now the theorem of Ekman says the following. It says that, and this theorem is a very easy exercise in linear algebra. Okay, it's not like the manifold case. We have that this thing, so, is the orthogonal subspace to Zj from before. Zj is going to be the orthogonal subspace of Vj, and more importantly, that this is true. Those subspaces are equivalent. Yeah. Dimension. Well, this is the one we defined here, this one is the one we defined here, and this is the space of J harmonic functions. So what is the space of J harmonic functions? We are not actually going to use it, but somehow this is what we are after. So let me define the Laplacian. The Laplacian, the J Laplacian, is going to be this. And note that even though we have here a lot of J's as well, this is actually, with those definitions, is something from omega J minus 1. Okay, so those are all the notations. This is the Laplacian that I'm going to use. H J that I wrote there is just the kernel so I need a full Laplacian, right? Yeah, okay, so I can define also, I'm sorry, this is just for defining what is the space of harmonic functions. We can also define the lower Laplacian, which is going to be, let me see now, I want to go down first. So this thing, I think, if I didn't make a mistake with the indexes. And then we can define the full Laplacian, which is just going to be the sum. And now Hj is the kernel of the Laplacian. All those things, which are just the functions which are generalization of harmonic functions on the graph, if you want. And this all the things here are generalization of what you see on graphs. And those are basically the Laplacians. And what I'm going to use is only the upper Laplacians. So you can forget about anything else. Basically, from everything that I wrote here, you only need to remember three things. The definition of this thing, the definition of the dual, and the definition of the upper Laplacian. Those are the things that I'm going to use. But this was a very, very fast introduction to theory of J forms on one forms on complexes. Okay, so this is the generalization of the Laplacian that I'm from now on going to just denote like that. And we are only going to be interested in one of them. So if we have a D complex, I'm going to be interested in this one, the upper one. So for example, on a graph, this is the Laplacian on vertices. Invariance is the Laplacian on edges, oriented edges, and so on. This is the one you're after. And we want to define the spectral gap, so let's see what is the spectral gap here. In the graph case, let me remind you, this is for graphs. We had the minimum of the spectrum of the Laplacian restricted to what is orthogonal to the constant functions. Why did we do it? Well, because we already know that the constant functions will always give us 0, and we want to avoid it. We want to ask about the one after it, and therefore we restrict ourselves to the constant one. And here we also know about something that is going to always give us something trivial. Well, since we have this decomposition, if we take something which is in the image of delta j minus 1, then we will have here a composition delta j minus 1 delta j, and this will always give us 0. Right? So if, in the general case, if f is delta j minus 1 of g, namely f is something here in, I hope I didn't do, yeah, okay. Then the upper Laplacian of f is going to be,
Interesting that in your notation, it should be delta j. You call delta j the one going from j minus 1 to j.
to j. Ah, okay, right. Should be, here it's, this is going from j minus 1 to
J.
j. Right. So,
To be honest, I don't know, there are many traditions. I always stick to give the index according to the
yeah, I think I tried to do it,
Otherwise,
but
nobody
somehow,
can remember.
yeah,
But
I
you
tried
do
to
it.
do it, but somehow I got
Okay,
stuck
that's
on-
good.
But okay, so
Don't put
I'm
any
sorry about the
index with
index
the right
problem, but
index.
the idea is clear, right? If I take something from the image of this one will give me a trivial 0. This will always be in the 0. I'm sorry about the index set, so it's vj minus 2. Just 1 second, let me see. So this is going from j minus 1 to j, so
Don't worry.
Okay, I think it's correct.
okay? Okay, and then if I did mistake, please check it. I will check it later. I'm sorry. But this gives a trivial 0, and therefore we want to restrict ourselves to the case where we are not in something that gives a trivial 0, and therefore we define lambda x. So I told you I'm going to restrict myself to this one. It's going to be the minimum, or if you want, we can put here j, but I'm going to always assume that j is d. Is the minimum of the spectrum of lambda plus d restricted to what is orthogonal to trivial zeros. And due to the theorem, this is the same as the minimum of the spectrum of this thing on the kernel from above. But so now we have all the definitions. We have h, we have lambda, we have the Laplacian. What the theorem that I stated before says that even in the I-dimensional case, we have that lambda is smaller than h if we have a complete scale. And now comes the question, what can we do in the case of a non-complete skeleton? And here is the conjecture we had. not a conjecture anymore, but so basically we have here, before the conjecture, let me write again the definition of H in the case of a complete skeleton. So we have the minimum of a partition into D plus 1 sets of the size of the number of vertices, the number of these cells with one vertex in exactly one of those. And here we have this multiplication of the size of the set. And somehow this comes from the fact that we have a complete skeleton, because basically the number of possible D cells that we can find is this number. Right? If we have this partition, the maximum number we can find is exactly this number, and therefore the conjecture we had was the following: define now for general complex h of x to be again the minimum over partitions into D plus 1 non-trivial sets. Here we have the size of phi. Here we have again the number of actual D cells we can find here. And now, instead of dividing by the number of possible in a complete skeleton, divide by the number of possible D cells in this specific skeleton. So we denote it like that. This is the number of possible D cells on the D minus 1 skeleton of these.
You don't mean A0 up to AD.
Yeah. No?
What do you mean? What's the difference between what is written there and what is written there?
This one? Okay, so let me.
This is the actual number.
This is the actual number you can find, and this is the
And this is the number that
you
are
can
possible.
construct. Okay, so let me draw a picture here. Let's do
This
this.
is
Possible.
Let's say
Or
that
possible provided the...
Given the D minus 1 skeleton.
given the D minus 1
I
skeleton,
see.
so let's say that our skeleton now is this thing like that. Okay, there are some edges missing, a lot, and we take some partition. Let's say this one, and this one. Okay, this is some partition. Now I can ask how many. Let's say that all the triangles I see are somehow here. So how many triangles do I have? I have this one, right? There is one vertex here, one vertex here, one vertex here, and basically that's it. But maybe I did it.
This number is going to be 1.
No, but what I wanted is that I will have No, I'm sorry. This is a bad example. Let's say that I also have this edge here. This is something I should think about in advance. But let's see if this will work. So now how many triangles do I have here? I have say this one, and let's say that this one here, let's say that I also have these edges, all three of them, but I don't have the triangle. So this one is going to be here. Okay, basically asking how many triangles can I construct, even if they are not there. Is it clear?
You can actually use a relative version of STEMI's method to do this. It's boundaries. So you associate, instead of face width, you associate the face module, then you can bound the number of triangles that you will see there, or high-dimensional faces, assuming the skeleton.
Yeah, exactly. What I'm taking X, which is a D complex, I'm looking on its D minus 1 skeleton, and now take all the possible D cells you can put on it. And I ask how many I can find in this partition. Okay? The picture is maybe misleading, but if the idea is clear, then basically, again, we take the D minus 1 skeleton, and now we take a completion of this into a D complex with as much possible D cells as possible, and we ask about what happens here.
This is a larger number than previously, than if you just use the product.
Yeah, this is large. Okay. But this is going to be exactly this thing when we have a complete skeleton. And now comes the theorem, which says the following. Let X be a general D complex. For a D minus 1 cell sigma, define for each D minus 1 cell and the partition, A0 up to AD, we define the degree of sigma in this partition to be the number of D cells in the completion of the complex according to this, which contains sigma.
What is this tau D? This is kind of upper D.
Yeah, this is basically the notation for what happens in the completion of the skeleton, of the D-1 skeleton that they used. I didn't change it.
This is, if you will, this is kind
If
of
I will-
the potential degree
Of
If I
this
will-
D-1 cell, if I will put all the possible. Okay, but it's a potential degree in this partition, and I'm only asking about cells, these cells which have one vertex in each of those sets. And define C of x. This is going to be the maximum over all the partitions possible over all possible D cells in the completion of the sum over all its subsets. Sorry, but there is no easier way that I know to write these things of this. So basically, I'm taking any partition, I'm taking any D cell that I can find in the completion, and I sum over the degrees of its D-1 subsets, and I ask about how large can this thing be. then lambda of x is bounded by, okay, we have here h of x, but we also have this. So this is the theorem. Let me remark that this thing is smaller or equal to 1. So it's actually better than the conjecture we have. And there are cases where it's strictly smaller than 1. Why it's less or equal to 1? Well, let's say that sigma is this thing, and let's say that, just for simplicity, that sigma I belongs to AI, and sorry, this is tau.
So this Cx, it's also depend on this F sigma, on this number of possible decels?
Yes, yes, here. The degree depends on it.
I know saw something. If we take the
Yes?
complex with bounded,
Yeah?
I mean, Cx over V goes to 0 even if we go to infinity. You know, Cx is not bounded, like can you get the degree?
No, the sum of the degrees.
But if the t minus 1 skeleton is already given,
Yeah, but if the skeleton is very big, then, okay, let me say what,
but of a bounded degree, let's take...
Yeah. Let's say that this is the one I do, okay? And without loss of generality, tau I is in AI.
Yeah.
So now I'm going over all its d minus 1 subsets. So let's remove tau 0 first. So now we have sigma, which is tau 1 up to tau d, right? This is one here, one of them. What bound can I give on its degree? This is the question, right? Well, the number of possible things is if we have from each one of those, so here we have tau 1,